Welcome to this week's video for SmartTut 5. Firstly, we will be looking at the exercises under section 1.8 and we are looking at number 12. It says, use the definition of continuity and the properties of limits to show that the function is continuous at the given number a. So before we can start, we need to know the definition of continuity. So the definition of continuity is that the limit as x approaches some number a of a function g of x equals the function value at that number a. So this is what we want to show is true. So we are going to look at the limit as t approaches 2 of g of t, which is the limit as t approaches 2 of t squared plus 5t over 2t plus 1. And we can then use the properties of limits to eventually write it in the following form. So we have the limit as t approaches 2 of t squared plus 5 times the limit as t approaches 2 of t over the limit as t approaches 2 of t, and we have a 2 in front there as well, plus the limit as t approaches 2 of 1. Now, the limit as t approaches 2 of t squared will simply be 2 squared. 5 times the limit as t approaches 2 will be 5 times 2. 2 times the limit as t approaches 2 will be 2 times 2. And the limit of a constant is just a constant itself. So we can now see that what we have here is what we would get when we would simply substitute the value of 2 into all of these places where we have t's in the function g of t. The actual value that we get here, if we work it out, is 14 over 5, and it is indeed equal to g at 2. And therefore, we have now proven that the function g of t is indeed continuous when t equals 2. Next, we are looking at number 17, and it says, explain why the function is discontinuous at the given number a. Sketch the graph of the function. So we have the function f of x equals 1 over x plus 2, and we want to explain why it's discontinuous at the value minus 2. Well, you should probably be able to recall from high school that this function is a hyperbola. And we know that this function has an asymptote at x equals minus 2. So, why is it discontinuous at the value minus 2? So, f of minus 2 is undefined. And if we were to sketch our graph, we know we have an asymptote at x equals minus 2. And then our hyperbola will look something like this. Next, we are looking at number 55, which says, use the intermediate value theorem to show that there is a root of the given equation in the specified interval, where we have the cube root of x equals 1 minus x, and the specified interval is the open interval from 0 to 1. So firstly, let's do the following. I'm going to say that f of x equals the cube root of x plus x minus 1. So I can obtain that function simply by taking the 1 and the minus x to the left hand side. So then I get the cube root of x minus 1 plus x equals 0. So I'm just setting my function f of x equal to this. I now want to show that f of x does indeed take on the value 0 in the interval from 0 to 1. The first thing I can say is f of x is definitely continuous on the closed interval from 0 to 1. In order to use the intermediate value theorem, I need to be able to say this. So f of x is continuous on the interval 0 to 1, the closed interval. And this is the case because we can substitute in any value in that interval without getting any problems. Then we know that f of 0 equals minus 1 and f of 1 equals 1. So basically what that says is that when we have an x value of 0, our function takes on the value minus 1, and when we have an x value of 1, our function takes on the value of 1. So by the intermediate value theorem, this means that somewhere in this interval, our function has to cross the x-axis. In other words, it has to have a root at some value c in that interval. So let's just write that out properly. Since minus 1 is less than 0 and 0 is less than 1, there is a number c in the interval from 0 to 1 such that f of c equals 0. So the value, at the value c, the function equals 0. And we can say this by the intermediate value theorem. Since the function takes on the value 0 at the number c, this means there is a root for the equation that we're working with in this interval. So thus, there is a root of the equation, the cube root of x plus x minus 1 equals 0, or in the form they originally gave it to us, the cube root of x equals 1 minus x in the interval 0, 1. And that's what we wanted to show. We are now looking at the exercises under section 2.3, and it asks us at number 37 to differentiate the following. F of t equals the cube root of t over t minus 3. So we need to use the quotient rule to differentiate this function. What does the quotient rule look like again? Well, if we have the quotient of two functions, f and g, and we want the derivative, it's going to be the bottom multiplied by the derivative of the top minus the derivative of the bottom minus multiplied by the top over the bottom squared. Okay. So let's now look at our function. So we want the derivative of f with respect to t. I'm just going to write my t, this cube root of t, as t to the power a third over t minus 3. So to take the derivative, it's going to be the bottom multiplied by the derivative of the top, which is a third t to the minus 2 over 3. And then I have minus the derivative of the bottom, which is 1, multiplied by the top, all over the bottom squared. And that's it. You can simplify it a bit further using a few more steps, and you can eventually end up with minus 2t minus 3 over 3t to the 2 over 3 multiplied by t minus 3 squared. We are now looking at number 55, and it says find an equation of the tangent line to the curve y equals x plus root x at the point 1, 2. So in order to find the equation of this tangent line, we definitely need the gradient of the tangent line at the point 1, 2. And then we can take this point and the gradient and substitute it into the equation y minus y1 equals mx minus x1 to find the equation of the tangent line. So let's first get our derivative. So it's going to be the derivative of x, which is 1, plus the derivative of the square root of x. Square root of x we can also write as x to a half. So it's a half, x to the minus a half. And this we can also write as 1 plus 1 over 2 root x. We are looking for the tangent line at the point 1, 2. So our x value is 1. So we want our gradient when x is 1. So that's going to be 1 plus 1 over 2 multiplied by root 1, which is 1 plus a half, which is 3 over 2. So our equation is going to be y minus, the y value we're substituting in here is 2. So it's going to be minus 2 equals 3 over 2, which is the gradient. And then we have x minus 1. And that we can also rewrite in the form y equals 3 over 2x plus a half. Finally, we are looking at number 88a, and it says find the nth derivative of f of x equals x to the n. So let's just first find the first derivative. The first derivative of f is going to be n x to the n minus 1. The second derivative is the derivative of the first derivative. So we still have our n, which is just a constant. Then it's multiplied by n minus 1. Then it's x to the power n minus 1 minus 1. So this is just going to become x to the n minus 2. Our third derivative is the derivative of the second derivative. So we still have our constant values n minus 1. And then we are going to multiply it by n minus 2. And we're going to have x to the n minus 2 minus 1. So it becomes x to the n minus 3. And you can continue on like that. So let's see if you can now spot a pattern. So what we have here is we are going to have n multiplied by n minus 1 multiplied by n minus 2 all the way up to n minus 1. Can you see if you look here? 2 is just 3 minus 1. 1 is just 2 minus 1. So in the case of the nth derivative, we have n minus 1, and then we have x to the, there's a little mistake there, that's supposed to be an n. It's n minus n, because for the third derivative we had a 3, for the second we had a 2, and for the first we have a 1. So for the nth we have an n. This is just x to the 0, which is just 1. This is going to be n minus n plus 1, which is just 1. So in other words, we have n multiplied by n minus 1 multiplied by n minus 2 all the way down to multiplied by 2 multiplied by 1. And this is simply n factorial. Finally, just one hint regarding number 7 in the TUT, which asks to prove that the limit as x approaches 0 of the product of x squared and cos of 1 over x squared is 0. So the hint here is that you want to use the squeeze theorem. So you want to try and find a function that is always less than or always takes on values smaller than the given function, and a function that always takes on values greater than or equal to the given function. Another thing to remember is that cos of anything always has to lie between -1 and 1. Or the absolute value of cos of something has to lie between 0 and 1. So try and remember that and use it in proving number 7. This is the end of this week's tutorial.